Good morning and welcome to today's CBER Best Seminar Series. Hard to believe we're on our last series of 2022. Today's topic is Bayesian adaptive validation design and extensions to vaccine surveillance. Before we jump into today's seminar, I want to remind you of a few Zoom logistics. My name is Kristen Koska, and I have the privilege of being the director at the Odyssey Center at Northeastern's Roux Institute, and we're really excited for continuing this discussion today. Now, you may notice the Zoom settings for today's seminar are all lines are currently muted. The webinar is recorded and will be disseminated later this week. Information will be shared at the end of this seminar on how to access that. If you want to ask questions while the presenters are sharing their material, there is a Q&A functionality in your Zoom taskbar. It's either at the top or the bottom of your screen, and you're welcome to submit questions there. As time permits, we will have the opportunity to have the speakers respond. You can also submit them in the chat functionality, and we will have somebody monitoring that. So now that all the logistics and housekeeping are sorted, it is my pleasure to pass it to Dr. Fan Bu, one of the postdoctoral research fellows on the CBER Best project, to introduce today's speakers. Fan?
Thank you, Kristen. I'm Fan Bu. It's my great pleasure today to be introducing our speakers, Dr. Timothy Lash and Dr. Lindsay Collin. Dr. Lash is the Owen Rollins Distinguished Professor of Epidemiology and Chair at the Department of Epidemiology, Rollins School of Public Health at Emory University. He is also the leader of the Cancer Prevention and Control Program of the Winship Cancer Institute at Emory University. Dr. Lash also holds a position as Honorary Professor of Cancer Epidemiology at Aarhus University in Denmark. Dr. Collin is a postdoctoral fellow at the Huntsman Cancer Institute working in the lab of Dr. Jen Doherty. She earned her PhD in epidemiology from Emory University, Rollins School of Public Health. The overarching goal of Dr. Collin's research is to understand multi-level contributors to disparities in recurrence and mortality among breast and ovarian cancer patients. In her doctoral work, Dr. Collin was awarded a National Cancer Institute F31 grant to evaluate the therapeutic changes, patient characteristics, and biomarkers that may explain variation in breast cancer recurrence among women diagnosed with breast cancer using Danish registry data. She has collaborated with the Georgia Cancer Registry and the Greater Atlanta Breast Cancer Task Force to examine race or ethnic disparities in breast cancer mortality in the metropolitan Atlanta area. She also has a strong methodological interest in Bayesian statistics, quantitative bias analysis, and efficient design of validation substudies. For her work at the Huntsman Cancer Institute, she has been awarded a TL1 postdoctoral fellowship, which aims to understanding the role of comorbidities and racial or ethnic disparities in ovarian cancer treatment response, and outcomes. Dr. Lash and Dr. Collin, we are very excited to have you here today, and we really look forward to hearing about your exciting research. Now I'm going to hand it over to you to talk about Bayesian adaptive validation and extensions to safety surveillance.
All right, thank you, everyone. So these are our COIs. In today's presentation, Tim will start us off kind of with an overview of validation study design and how they're used to inform bias analysis, with a brief illustration of the balance design and cost efficiency methods. Then I'll talk a little bit more in detail about the framework for the adaptive validation design, with specific examples on the flexibility of stopping criteria, applied examples, and then future directions of this work.
Okay, thank you, Lindsay. And it's very nice to be here today. So I think just to set some common ground, brief review of information bias. This occurs when some variable of interest in an analysis has been inaccurately or imperfectly measured. And there are long-standing, long-known methods to bias adjust for those imperfections for classified variables, either using sensitivities and specificities or predictive values. Next slide. So here's a 2x2 table starting with, which is just cross classification of exposure and disease. And on the left is what we would ideally measure if there was no imperfect measurement. That's the truth. And we can estimate or what we expect to observe given sensitivities and specificities. So here, for example, looking at the exposed cases, which we've notated capital A, what we expect to observe, the number of exposed cases, lowercase a, is a function of the sensitivity and the number of truly exposed cases. So that's the proportion of correctly classified with regard to exposure. And their complement is incorrectly classified as unexposed. And then we add to that the complement of the specificity times the truly unexposed cases. And so that's what we expect to observe. And you can sort of think of this as signal being the part coming from capital A that we recover, and noise being the mixture in with truly unexposed people, which is a function of specificity. Next slide. But of course, we don't start with the truth. We start with an observation. So retaining the lowercase notation, that's the table now on the left. And one way to bias adjust to get back to an expected truth is using predictive values. And so we can recover an estimate of the number of truly exposed cases A by using positive and negative predictive values within strata of cases and non-cases. Next slide. You only see the equation on the left because the number in the right column, the unexposed column, we can just calculate by difference. So that's why the equations are just in the left. Next slide. A second way to recover an estimate of the expected truth is to use measures of sensitivity and specificity. So this is just an algebraic rearrangement of the first 2x2 table that you saw, where we're solving for capital A, given an observed number of exposed cases, lowercase a, and estimates of the sensitivity and specificity. Next slide. So that's the algebra. The hard part in bias analysis is providing estimates for the sensitivity and specificity or the positive and negative predictive values. These are always going to be measured with some uncertainty. And in my view, the best way to do that is with some sort of internal sub-study, which could be by design, some sub-study in which we're estimating the concordance between the imperfect measure that we have on everyone and the gold standard that we have on a subset. Sometimes this subpopulation might be naturally occurring. For example, if some multi-site study has both the imperfect measurement and the gold standard in everyone, then we can take advantage of that as an internal sub-study that's naturally occurring. If you can't do an internal validation study, then we have to borrow information from similar studies and similar populations or make educated guesses. I think it's important to remember, though, that despite the imperfections and uncertainty in these validation data, if you don't do this, then there basically is an implicit value where you assign sensitivity and specificity of 1, for example, which is the value that you most know is wrong. Next slide. So a lot of what we're going to talk about today is how to design these internal validation sub-studies. And they are expensive, because if the gold standard weren't expensive to collect, then we would already have it on everyone. So usually the reason that we don't have the gold standard measurement is that it's expensive to collect. And so we invest only a smaller proportion of the study's resources, time, and money to collect better information on just a subset. Next slide. So this always involves sampling. If the validation data, if the gold standard was available on everyone, then we wouldn't have to take account of the imperfect measurement at all. And who is sampled to participate in the validation study and how many participants there are in forming the parameters has consequences for what can be estimated and how precisely it can be estimated. Next slide. Now, it turns out that there's actually not a lot of training in how to conduct internal validation sub-studies. My colleagues, Matt Fox and Lisa Bodner, and I did a sort of convenient sample of epidemiologists to see what they knew about validation sub-studies. Next slide. And the key findings were that only about a third had ever designed a validation study, and only about a third said that their doctoral training had included information about validation study design. Only about half said that they were confident that they could design and implement a validation sub-study. So I think this is a gap in training. Many people don't encounter the information and therefore don't feel confident that they could design a validation sub-study. Next slide. So let's show you one way to design such a study. So we'll start with this clearly synthetic data that I've made up, where we have a cohort of 100,000 people, 10,000 or 10% exposed, the remainder unexposed, and the risk in the exposed is 3 times that in the unexposed. Next. Now let's imagine that the exposure has been misclassified with 60% sensitivity and 90% specificity. Then the table that we would expect to observe is shown on the right, and you see that, as expected with non-differential misclassification of this dichotomous exposure, the risk ratio is biased towards the null. So what we'd expect to observe is 1.65. And what we'd like to do is to design a validation sub-study that would allow us to recover the estimate of 3. Next slide. And so this is just an example of how we get to the number 81. Is the sensitivity times 90 and 1 minus the specificity times 270. Next slide. We can also calculate then what the predictive values are, positive and negative predictive value in cases and non-cases. And of course, these have to be stratified by disease status because given the causal influence, the exposure prevalence is different in cases and non-cases, and therefore the predictive values differ in cases and non-cases. Next slide. And these are just the ways that we've calculated each of those. Go ahead. So it is typically tempting to conduct a validation sub-study in a simple random sample. That's, guarantees you some representativeness, expectation of representativeness. And so it is oftentimes what we are tempted to do, but it turns out to be highly inefficient. And I'll show you why. So if, for example, we take a 10% sample of the whole population and then divide it into strata of cases on the left and non-cases on the right, you see that the validation study in cases involves only 36 people, whereas the validation study in non-cases involves closer to 10,000 people. So right away, there's this huge information imbalance between cases and non-cases because we've taken a simple random sample. And that trickles down to both inaccurate estimates of the parameters, just because people appear in integers. And so when only 36 people are included, we don't get accurate estimates of sensitivity or specificity or positive or negative predictive values in the cases, and we get really wide intervals around those proportions. Whereas in non-cases, we get very accurate estimates with very accurate intervals. The problem is the bias adjustment requires good measurements for both cases and non-cases, and we have fallen short on providing that for cases. Next slide. So the solution oftentimes is to do what's called a balanced design. And that is we take the smallest cell frequency in the observed data, and that was 81 exposed cases. And we take all 81 of the exposed cases into our validation study. And then we sample within strata of exposure and disease, 81 people from each of the other 4 cells. So now our validation study has 324 people in it instead of 10,000 people in it. And we actually recover accurate estimates of positive and negative predictive value in both cases and non-cases, and equivalent with intervals for both cases and non-cases. Now, the price that you pay is you can't estimate the sensitivity and specificity, and that's because by design, we fixed the margins of exposed to unexposed at 1:1, whereas it's closer to 10:1 in the actual source population. With reweighting, you could correct for that, but the validation study data itself provide only an accurate estimates of the predicted values. Next slide. You could also sample based on the truth. This is unusual because we don't usually have the truth on everyone, but if you have a naturally occurring sub-study, then you could sample based on the truth, and then the opposite would occur. You'd have accurate estimates of the sensitivity and specificity with equivalent with intervals in cases and non-cases, but because you fixed the margins of the columns at 1:1, you don't get accurate estimates of the positive and negative predictive values. Next. So an extension of this, and what Lindsay is going to tell you about, is adaptive design, where because these validation studies inherently involve sampling and added expense, you can conduct the validation study longitudinally, and as the data accumulate, you can evaluate the data and decide whether or not to continue the validation study using stopping rules like pre-specified criteria for when the bias parameter has been measured well enough, when the bias adjusted estimate is measured well enough, or when there's a good reason to stop or decide that it might be futile to continue to validate. So foreshadowing a little bit of what Lindsay will talk about. Next. And I will close by just saying that there are also ways of calculating validation designs that explicitly take account of the cost of collecting the validation data. These don't incorporate right now the adaptive strategies that Lindsay will talk about, but they do take account of the trade-off between accumulating, for example, more people into the main study versus accumulating more people into the validation study. And so these are just some citations as a resource in case you're interested in that method. And with that, I will close and happily turn over to my colleague, Dr. Collin.
Thank you, Tim. And thank you again, everyone. Okay, so I'm going to spend a little bit more time talking about the adaptive validation design, as well as specific examples of stopping criteria that could be implemented. So as Tim mentioned, most guidance on validation sub-study design really pertains to studies that have completed enrollment and follow-up, and typically involve the simple random sample or balanced design. But oftentimes, investigators may want to collect validation data simultaneous with cohort enrollment and follow-up, or collect validation data until specific stopping criteria are met. The goals of validation vary from study to study, so thinking up front what the goals of validation are can make the implementation of the adaptive validation design more amenable to different stopping criteria. So the main motivations for the adaptive design were to guide validation efforts that could occur simultaneous with cohort enrollment and follow-up, and that were amenable to various stopping criteria, such that investigators could monitor validation data to meet the goals of validation. In general, it uses the framework of Bayesian monitoring techniques that were developed in the context of clinical trials to monitor treatment response over time. In our approach, we extend this to monitor validation data as they're collected to meet the goals of validation. So we use a Bayesian framework for this, and I'll talk about it in general terms, but I will also acknowledge that you could also use a frequentist approach to this. Just mathematically and intuitively, a Bayesian approach makes a little bit more sense, at least when we were developing the design. So we start with a prior, which would be some knowledge about the classification parameter of interest. And then at each iteration of the validation approach, we update that parameter over time until the goals of validation are met. And again, these classification parameters are the positive and negative predictive values, or measures of sensitivity and specificity. Oftentimes, we'll start with a uniform prior, which means that we assume that all values of the classification parameter are plausible. And so for this, we operationalize as a beta 1, or where alpha and beta are equal to 1. This will be most applicable to measures of positive and negative predictive value. For measures of sensitivity and specificity, if there are other published validation substudies, you could probably state that certain values are more likely than others. We then update the parameter in blocks of participants. In the examples I'll show, this mimics a balance design that Tim was talking about. And we, for these records, typically use a study sample size of 20. So this would be the 2x2 classification table that we would observe at each iteration. If it's a dichotomous exposure or outcome variable that's we suspect is misclassified, it follows a binomial distribution. And then the updated classification parameter follows a beta distribution with alpha and beta parameters then being updated to reflect both the prior and the validation data collected at each interval. So we kind of update this in an iterative fashion. And this is just another way to show how we're updating the classification parameters over time. And so the posterior or the updated classification parameter is a function of the collection of validation data at the previous time points as well as the prior. So those are kind of the general aspects of the adaptive validation design. And now I'll go through 3 examples that we've implemented this framework with various stopping criteria. So the first is based on the precision of the classification parameters. This may just be to have confidence in the positive and negative predictive values or sensitivity and specificity estimates. The second is an example of efficacy or futility of validation. So this is how well does the potentially misclassified variable capture the gold standard, if at all. And then thinking back to kind of incorporating bias, these parameters into bias analysis based on the precision of the bias suggested estimate of association. So in this example, this is in the context of colorectal cancer. And for those of you who aren't familiar, it's third most commonly diagnosed cancer and the third leading cause of cancer-related mortality globally. Despite improved survival, the 5-year risk of recurrence is quite high, with an estimated 20 to 50% of colorectal cancer patients developing recurrence. And this is clinically relevant endpoint. However, it's not captured by most population-based cancer registries. So algorithms have been developed to try and collect colorectal cancer recurrence data using a combination of different data sources. So in this example, we want to show how using the adaptive validation study design could be used to model when sufficient validation data have been collected to validate colorectal cancer recurrences identified through an algorithm. The study population includes Danish colorectal cancer patients who underwent surgery and were registered with the Danish colorectal cancer group database. And then patients were enrolled and actively followed for colorectal cancer recurrence. So in this subset of the study, 355 individuals, the gold standard was available on everyone, and 63 recurrences were identified. Tim and some colleagues in Denmark previously developed and validated this algorithm in the Danish colorectal cancer group database. And so here we're showing how the adaptive validation design could be used to validate the algorithm as well. Here we implement 2 validation substudies. The first is what you would expect to see in a typical validation sub-study. Here we sample based on the algorithm-defined recurrence, which we suspect is susceptible to misclassification, and validate against the gold standard follow-up. Again, this allows us to estimate the positive and negative predictive value. And in the second, we sample based on the actively followed cohort and compare with the algorithm-defined recurrence. And this allows for estimation of sensitivity and specificity, but in practice is a little bit more challenging because we don't often have this naturally occurring subset of the population with the gold standard available for everyone. Our stopping criteria were based on a predefined threshold value and level of precision. We wanted to accurately classify recurrences and non-recurrences, which is why we established a threshold value. And then we want precision in that classification parameter. I will say that these two are highly correlated, meaning that if you have a high threshold value, you typically also have to have a very precise estimate just because of the bounds between 0 and 1 for the classification parameters. For positive and negative predictive value, we established a threshold where the lower 95% credible bound for positive and negative predictive value had to be above 0.8, and we allowed for a precision of 0.15, which is the upper minus the lower credible bound. For sensitivity and specificity, we established a slightly higher threshold value of 0.9 and precision of 0.08. So in general, you want these informed by, again, the goals of validation and then subject matter knowledge. And this is kind of a framework for the adaptive validation sampling strategy. We wanted to simulate this as if it were occurring in real time. So we ordered based on the timing of recurrence, and we would sample 10 with and 10 without a recurrence identified, and validated 20 records at each iteration. This allows us to then estimate the classification parameters, and then this process is repeated until the stopping criteria are met. And these are a summary of the results. So for complete data, we have 355 participants. We have estimates of positive and negative predictive value of 0.86 and 0.99 respectively. Using the adaptive validation approach, 120 records were necessary to meet the goals of validation. And we see that the positive predictive value is 0.9, a little bit higher than from that obtained with complete validation data, which I'll show what we think may be happening there, and then a negative predictive value that's fairly comparable. For sensitivity and specificity estimates using complete validation data, we have estimates of 0.95 and 0.97 respectively. Again, 120 records were necessary to meet the goals of validation, and have pretty comparable estimates for the adaptive validation approach. So we can look at how these estimates are changing with each iteration of the adaptive validation approach. We see, as expected, at the first iteration, they're quite wide confidence limits and imprecise. And then over time, both the positive and negative predictive values become more precise and increase a little bit, at least in the middle iterations. So one thing we notice is that the positive predictive value was lower when we use the full study data compared with when we stopped with the adaptive validation approach. And this, we actually think may be due to loss to follow-up in the study cohort rather than the algorithm not performing as well over time. So it's kind of an interesting finding from the adaptive validation approach. Here, again, shows the estimates of sensitivity and specificity as they change over time. Again, starts very imprecise and gradually becomes more precise and similar to the complete study population toward the end. So in this example, we showed how classification parameters were estimated using the adaptive validation approach were fairly similar to those obtained using complete study data. Some considerations when implementing this type of stopping criteria in your own study is that stopping criteria should be based on subject matter knowledge and the goals for validation. Here we showed estimates of positive and negative predictive value for the outcome overall, but if these parameters are to be used in a bias analysis, then you would want to estimate them within straight out the exposure. And we were able to show sensitivity and specificity here because we had a subset with the gold standard available for everyone. However, in practice, this may not be the best approach. And the number included at each iteration is also something to consider when implementing. We, through kind of the development of this design, have found that a sample size of 20 at each iteration is a good balance between being able to monitor validation data and to not have too much random variation. However, this would likely depend on what is required to validate the records. This could be based on how many records are able to be validated during the day or a week. And then if it's an assay that's required for validation, it may have to do with the cost of the batch or running the assays. So in the second approach, this is stopping based on efficacy or futility of validation. In this example, we're using the study of transition outcomes and gender or strong cohort, which was established to understand the long-term effects of hormonal therapy on transgender and gender nonconforming children, adolescents, and adults. It's an electronic healthcare record-based study of individuals from Kaiser Permanente health plans in Georgia, Northern California, and Southern California. And the study population includes around 1,300 transgender and gender nonconforming children and adolescents, and 4,700 adults. So here we're interested in validating the exposure. The exposure of interest was transmasculine or transfeminine status, which can be determined from knowledge of sex reported at birth and current gender identity. I do want to acknowledge that binary gender definitions are suboptimal. However, for the purposes of this study and for the example of the adaptive validation, we assume that someone whose gender identity differs from female sex recorded at birth would be transmasculine, and someone whose gender identity differs from a male sex reported at birth would be transfeminine. In this study, the misclassified sex reported at birth variable was based on the recent electronic health record. And it's known to be misclassified because it could either represent the sex reported at birth or current gender identity. So the EHR data available for Kaiser on each of the individuals identified have a gender code, and we're not sure if that reflects their current gender identity or their sex reported at birth. So the STRONG study team validated these records among those who were over 18 years of age as of January 1st, 2015, which was about 40% of the youth subcohort and the entire adult subcohort. Here again, we show the classification parameters for positive and negative predictive value and negative predictive value for transmasculine and transfeminine status. The labels for positive and negative predictive value for transmasculine and transfeminine were made at random. But just to clarify, the positive predictive value is defined as the probability that sex reported at birth in the gold standard medical record was female among those whose sex reported at birth in the concurrent EHR data was female. Negative predictive value, therefore, was defined as the probability that the sex reported at birth in the gold standard medical record was male among those whose sex reported at birth in the concurrent EHR data was male. Here, our stopping criterion is based on a predefined threshold value. Again, we're mainly interested in understanding whether or not the concurrent gender code in Kaiser reflected sex reported at birth accurately. So we established an efficacy criterion that's for the positive and negative predictive value, where the lower 95% credible bound was above 0.6, and futility would be determined if the upper 95% credible bound for a positive negative predictive value was below 0.6. Again, our sampling strategy is based on the order of cohort enrollment. And then we sample 20 at each iteration. We validate the gender code, which allows us to update the positive and negative predictive values. And these are a summary of the results. So in the use of cohort, we determined that validation efforts were efficacious. So for the complete study data, we have estimates of positive negative predictive value of 0.92 and 0.81. 535 records were validated, and this was over the entire study period. Using the adaptive validation design, 120 records were necessary to meet the goals of validation, and our estimates for positive and negative predictive value were 0.87 and 0.71. And this was 700 days into the study time period. One thing that we noticed is that the estimates for positive and negative predictive value were substantially lower than those observed in the complete study data. And that's something we looked into further, which I'll show over the next couple slides. For the adult subcohort, using complete study data, the positive and negative predictive values were 0.5 and 0.6 respectively, and that was estimated over the entire course of the study period. So estimates for positive and negative predictive value of 0.5 and 0.6 really illustrate that the gender code for Kaiser was kind of a toss-up of whether or not it reflected the current gender identity or their sex reported at birth. So the strong investigative team, rightfully so, ended up validating all of the adult sub cohort because this variable did not accurately capture the gold standard. The adaptive validation approach also detected that after the first iteration, 3 days into the study time period. So here we show for the use subcohort, the estimates over time with the adaptive validation approach. And again, this shows not only are the estimates getting more precise with each iteration, but they're trending upwards, which suggests a time trend in the classification parameters. In the adult subcohort, this, with each iteration, the adaptive validation approach also shows that these are not accurately capturing sex-reported error. So I mentioned that there was a time trend observed for the classification parameters in the use subcohort. So one thing that we did to investigate this further was to do a single person validation effort. And that means that we updated the beta distribution for the classification parameters with each individual as they were enrolled into the study time period. So these show the distribution for positive and negative predictive values. Generally, what we would expect for these distributions is that after about 20 records were validated, we would have kind of a wider peak, and then it would increase at the center of that over time as we get more data. However, what we see here is that that first peak for the positive predictive value is around 0.5, but then it migrates over time and ends around kind of 0.95. So that suggests that there's, over the course of the cohort enrollment, which is about 10 years, the way that the gender code was recorded in Kaiser was changing. So initially it seemed that it could have reflected gender identity or sex reported at birth, but then over time was more likely to reflect sex reported at birth. And we see the same thing for negative predictive value. But the important thing here is that the time trend is probably something that would happen in other studies as well, and you wouldn't be able to capture that with the simple random sample or a typical balanced design. So a summary of this example, we demonstrate how this method could be used to determine efficacy or futility of validation, optimizing study resources concurrent with cohort enrollment and follow-up. Some considerations for this is that efficacy or futility should be consistent with the goals for validation. And prospective monitoring of validation data allowed for detection of a time trend, which would not be captured by other designs. This may change, the detection of a time trend may change your approach to validation substudy design, especially if you're trying to use these parameters in bias analysis. So in this next example, I'll talk more about if the goals of validation are to be used in quantitative bias analysis and how you may sample validation data to be consistent with the precision of the bias-adjusted estimate. So here our stopping criterion is based on a pre-specified level of precision. Again, we're going to use the strong cohort. And here we're looking at the association between transmasculine or transfeminine status and self-inflicted injury in the use subcohort. So the sample of 1,300 individuals. Again, we're estimating the positive and negative predictive value as before, but now because we're interested in association, we compute the positive and negative predictive values within strata of the outcome. And again, our stopping criterion is based on the precision of a bias-adjusted estimate. Because our confidence limits are now going to account for measurement error and random error, we know that we're going to lose a little bit of precision. And so we allow for no more than 80% wider than the conventional estimate. This contingency table shows the conventional estimate with an odds ratio of 1.99, indicating that transmasculine children and adolescents are about 2 times more likely to self-inflict harm compared with transfeminine children and adolescents. The precision of the estimate is the upper minus lower confidence limit, which is 1.99. And if we allow for 80% wider or a little bit loss of precision, that's going to lead to a ratio of 3.6 for the upper minus the lower confidence limits. In order to compute the precision of the bias-adjusted odds ratio, we need the variance of the bias-adjusted odds ratio. Luckily, this was previously derived by R.J. Marshall back in 1990. I won't go into details on his derivation, but I do recommend this paper. And in sum, I'll say that the variance is dependent on the size of the study, like the full cohort, and then the size of the validation substudy, the classification parameters, and the prevalence of the exposure within strata of the outcome. Again, this is illustrating our sampling strategy for the adaptive validation approach. The only difference here is now we're sampling 40 records at each iteration, and this is largely because we're computing positive and negative predictive values within strata of the outcome. And these are a summary of the results. So here our conventional estimate, which assumes perfect classification of transmasculine and transfeminine status. In the adaptive validation approach, 117 records were necessary to meet the goals of validation. Our bias-adjusted odds ratio is 1.4 with interval 0.77 to 2.52. If we compare those results with the results that would have been obtained using complete validation substudy, we see that the bias-adjusted odds ratio is fairly comparable with an estimate of 1.47 with interval 0.95 to 2.26. It is more precise by design because there are 535 records that were validated. We also see that the estimates of positive and negative predictive value are fairly comparable across the adaptive validation approach and the complete validation set. This is just illustrating the p-value functions over time. The red line indicates the conventional estimate, which is centered at 2. It's more precise. And then we see from the blue line to the purple line, the iterations of the adaptive validation approach, and then we compare that with the p-value function or the orange line that's using complete validation data. In general, we see that all show a bias away from the null for the conventional estimate, and the adaptive validation approach is fairly comparable to the estimate obtained using complete validation data. So in summary, the bias-adjusted odds ratio computed was fairly comparable, although less precise than the bias-adjusted odds ratio that would have been obtained using complete validation data. Some considerations when using this as a stopping criterion: it's important to define an acceptable level of precision that will yield substantively meaningful results. The example we showed led to a fairly imprecise bias-adjusted estimate, and that's largely because of the smaller sample size of the cohort and fairly rare outcome. But in other studies, you may want to use more precise estimate as a stopping criterion. And then oftentimes when we're doing a bias analysis with these classification parameters, we want to implement probabilistic bias analysis. And this allows us to account for confounding, random error, and measurement error. But this kind of framework for the adaptive validation design gives you that initial stopping, which then you can then use more advanced bias analysis techniques moving forward. So some conclusions and future directions. So in example 1, we showed how you could use the adaptive validation design with stopping criterion that's based on a threshold value and pre-specified levels of precision. In example 2, we illustrated how you may use this method to determine efficacy or futility of validation, which could optimize study resources. And in the third example, we illustrate how you could use this in the context of precision of the bias-adjusted estimate. Some general advantages of this approach: it offers a framework for validation substudy design suitable for scenarios in which validation data are collected in real time and applicable to any parent epidemiologic study. It allows researchers to allocate fixed study resources when implementing validation sub-studies. And our method outlines an approach for study design based on precision. Some future directions of this work. One is in both of our first 2 examples, we noticed a time trend in classification parameters. And that's not something that's been documented in the literature before. And so we're trying to work to understand how you may want to guide validation sub-study design in the presence of a time trend in classification parameters, and then also how you may want to incorporate that time trend in a bias analysis. Another important aspect of the adaptive validation design is you may be able to stop validation efforts earlier, or at least that's the goal, than you otherwise might. But oftentimes researchers are interested in what's the probability that your inference would change if you collected more data. So that's another aspect that we're working on. And then finally, in larger cohorts, thinking about information-rich samples. So who would be the next best group for validation efforts. And then kind of conclusions, our group is thinks that more time and effort should be put into thinking about effective and efficient validation study designs in the context of epidemiologic studies. And then we'd like to acknowledge our wonderful collaborators and then funders, and happy to take any questions.
Wow, Lindsay, I couldn't keep up tweeting because you had so many great findings. And I just want to say thank you, Tim and Lindsay. This was fantastic. I certainly feel like I have a lot It looks like in the chat, a few folks in the Q&A were kind of curious about, we said validation and validating in general context, and then we applied it within this study. So maybe we could just sort of just recover that. I think you said it in your examples too, but doesn't hurt to be specific, since we use validation a lot in many different levels of application. Maybe study by study, or I'm not sure, but it looks like someone wanted to articulate what is being validated in the validation study. It looked like it was specific endpoints, but I don't know. Sorry, Tim, I didn't mean to cut you off.
Sure. So, I mean, the general idea is that you have a variable that is imperfectly measured, for example, colorectal cancer recurrence. And it's being in the entire cohort, it was for all colorectal cancer patients in Denmark over the specified period, there was a registry-based algorithm that guessed whether or not their colorectal cancer had recurred. For example, was there new use of chemotherapy? Had they been admitted to hospice? So these were like suggestions that there had been colorectal cancer recurrence. There's not an actual record of medical record review or pathology saying there had been a colorectal cancer recurrence. So that's in 20,000, I think, colorectal cancer patients. It just so happened that we had this actively followed cohort of colorectal cancer patients, 355 of them, where every 6 months they were going to their surgeon and being evaluated for whether or not they had recurred, like active surveillance. And so for those patients, we had this gold standard measure because of the active surveillance that they had a recurrence. So for those 355, we apply the same algorithm, which makes a guess of whether or not they recurred. And that's the same guess that's used on the whole 20,000. But for all of the 355, we also have this gold standard of active medical follow-up for recurrence, and that's the gold standard. So it's the comparison, it's the algorithm's guess of recurrence that's being validated by active surveillance by a physician, which is the gold standard. That's the expense, right? You can't do that for 20,000 Danish colorectal cancer patients. Common exposure is tobacco use, typically collected by self-report, which is cheap and easy, but we know that it's imperfectly self-reported. So current tobacco use, you can validate by collecting just about any biospecimen and measuring cotinine in it. But that's expensive because you have to collect the biospecimen and do the bioassay. So you can't do that in everybody. So those are two examples of why imperfect measurements are usually collected, because they're cheaper and easier to collect on a large group. The validation data are collected because it's expensive and time consuming. And so you want to do that on as few people as possible to optimize the use of study resources. And that's where Lindsay's adaptive validation, I mean, you could see that in both the recurrence example and the transgender example, she was able to reach the same kind of estimates with far fewer people than had been included in the original validation study. Lindsay, anything to add? I don't know.
No, I think that was good. I mean, I think in the context too of vaccine surveillance, you could say the same if you're collecting vaccine self-report information. Oftentimes that's misclassified, so you want to compare with medical records most often, and with any outcome associated with that vaccine self-report versus the medical record.
That makes a lot of sense. I can't believe it's not practical to do 20,000 people for something it's just wild. There's a great question that came in while you were answering that around applying this within the context of diagnostics. And I kind of heard that alluded to when you said based off of assays that you might be running. And I don't know if there are suggested researchers. It looks like someone's looking for maybe additional reading. They want to do some homework on this space. So do you have any comments on that?
Outcome validation?
in diagnostics in particular, it looks like folks are curious if you have recommendations, if that's their interest, if you have any directions for them to kind of read up in the field.
Yeah. So this work actually began on this topic for drug and vaccine adverse events. And so, very commonly they're registry-based studies using claims data or something where there's an ICD code for an adverse event. And it's kind of widely agreed that that might be imperfect. And so the typical strategy then is to do a medical record review of a subset to see how accurate the ICD codes are for the adverse event of interest. But that's expensive, right? You've got to pay for an abstractor to go and read the medical records. And so you want to do as little of that as possible before you can move on. And that might be, as Lindsay said, because you can find the ICD codes are just futile, which we did find an example where they were not informative. But you might also learn what you need to do the bias adjustment to correct for the improper or imperfect ICD codes. Further reading, Lindsay?
So your quantitative bias analysis is good. I think on like the actual diagnostics kind of early work in this, like Donna Spiegelman's papers.
Yeah, the Holcroft and
Really
Spiegelman
great.
paper.
Yeah, I think a lot in nutrition, which obviously is an area that has a lot of potential misclassification depending on how you're measuring it. And I think one thing to keep in mind is sometimes the gold standard isn't necessarily, a lot of times it's through medical record review, but even defining the gold standard in certain areas can be more challenging than others. So that's something to think about upfront when you're designing that validation study.
That makes sense. Well, I won't keep you in the hot seat any longer than the top of the hour. We're really grateful to have this presentation to conclude. I see a few questions about extending things to survival data. I'll let those folks, I'll ask you questions offline. And for those of you who are attending, if you're interested in following the series, I'm going to put a link in the chat. The BEST website will continue to be updated with next year's plans. Thank you, Lindsay and Tim, for helping us wrap up. I have some homework to go read up on your cohort studies. This was truly wonderful. And we can't wait to maybe invite you back in a future year. We're going to end the seminar for today, and
thank you.
We look forward to making these materials available on demand. Signing off.
Bye-bye.
Thank you.